All right. So we're almost done. We've got one more exercise, two more exercises. Permutations and combinations together, which is what we're going to do now, which I think is a hard one because it's not just is it permutations or combinations, but rather really thinking through. So we're going to look at that. And then probability with permutations, which is much easier, but we'll look at that one as well. So starting off, this is permutations and combinations. And really, it's just giving us scenarios that we have to figure out how many ways can this occur, and they utilize either permutations or combinations. So this one is putting your reindeer in a single file line. All right. Now, like I said, these questions are not as straightforward as the previous two exercises of just permutations by itself and combinations by itself. So let's read it and kind of try to figure out what's going on. It says, you need to put your reindeer, Balthazar, Rudy, Jebediah, and Ezekiel in a single file line to pull your sleigh. However, Ezekiel and Jebediah are best friends, so you have to put them next to each other or they won't fly. So you've got four reindeer. You've got Balthazar, you've got Rudy, you've got Jebediah, and Ezekiel. Which, if there was no constraint, the number of ways that we could arrange them would be 4 factorial as a permutation if the order mattered, or we could use the combination formula, which would still just be, 1. There's only one way to organize all 4 of them, but we'll get to that later. 4 factorial would be the way that we could organize all of them. However, because they're saying Ezekiel and Jebediah have to be next to each other, we can kind of just group them as one object. So really we're talking about 3 unique items, and the number of ways to arrange 3 objects would be 3 factorial, which is 3 times 2, technically times 1, which is 6. So there are 6 ways that we could put these elements in different orders. Maybe Balthazar goes first, then our group of Jebediah and Ezekiel, and then Rudy, or Rudy goes first, and then Balthazar and Jebediah and Ezekiel are at the end. Either way, 6 ways. But 6 is not the answer. Because in our Jebediah and Ezekiel group, we could flip their order. So for all 6 of the ways that we could order these, there's another grouping where Jebediah and Ezekiel are just flipped. They're still next to each other, but they are in the opposite order. So the total is going to be our 6 ways of arranging them that we found through factorial, and then multiplied by 2 for the different ways that we could arrange that, which would be 2 factorial, technically. So our total ways here is 12. That one wasn't too bad. They get worse. How many numbers between 1 and 100 are divisible by 3 or 4? So we can figure this out since we're just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. by division. 3 goes into 100. 33.33335. Right? I just need the integer. There are 33 numbers from 1 to 100 that are divisible by 3. You're just counting them off, really. So we're just saying how many segments of 3 can we break it up to. So that's 33. Then, for 4, we know 100 divided by 4, it's 25. So we're going to add that, 25. And that should be the total, right? 33 plus 25, 5, 6, 7, 8. So 58. 58 numbers. But we're over-counting because there are some numbers from 1 to 100 that are divisible by 3 and 4. So we have to be very careful with statistics. That's really what this is trying to do, is get you to recognize that statistics is a very nuanced mathematics. You have to be careful how you're counting things, or you'll throw your statistics off. Although these are complex problems, and I'll be the first to admit I'm not great at statistical thinking. I know how the math works, but the first time I ran through these problems, I forgot about the overcounting. So it's 58, and I got it wrong because I forgot about numbers like 12 and 24 and 48, numbers that are divisible by 3 and 4. In fact, 12 was a good example, because if a number is divisible by 3 or 4, it's also divisible by 12. And those are going to be my overlaps, because 12 is 3 and 4. So I need to look at the numbers that are divisible by 12. We can kind of do it the same way. 100 divided by 12 will tell me how many multiples of 12 there are. So let's see that one. That's 8.3. Again, we don't need the decimal part, we just need the 8. So we're going to take those 8 away. And so there should be 50 numbers that are divisible by 3 or 4, but not both 3 and 4. Not overlapping, or not counting those overlaps twice. So we're going to take away the 8, it's 50. 50 numbers. Good. Another way to do this problem would be to actually just list the multiples of 3 and 4, and then you would see the overlap. 12 would appear twice in the list. 24 would appear twice in the list. And you could say, oh, okay, I don't need to count those twice. Okay. But division is a quick way to say how many things, how many of this amount of things can I take out of this larger amount. 100 divided by 3 tells me the number of groups of 3, which is also the multiples. All right. So then these again. The word pretty, P-R-E-T-T-Y. There, so P-R-E-T-T-Y. Now, we saw something like this in the permutations exercise. It's giving me a word, but really just letters. It wants me to figure out how many ways are there to arrange the letters. That's a permutation. Order matters with letters. So look, there's 1, 2, 3, 4, 5. There's 6 letters, so it should be just 6 factorial. However, we have kind of a problem here, in that these are able to switch places without actually affecting the rest of the letters. So we need to get rid of that. We need to divide that out. Okay. So really, out of that 6 factorial, 4 of them can move around, but those 2 factorial need to be divided out. Because it's not going to give me a unique ordering. It's just going to give me so 6 factorial over 2 factorial. We could have done the same thing that we did with the reindeer as well, and just say, well, these are grouped, and then figure out how many different ways we could arrange that. But it's not together, it's just that if they switch places. So we definitely want this 6 factorial over 2 factorial. We could be using the combination formula too, but I don't think we want to divide out the 4. I think it's just this. So that's going to be 6 times 5 times 4 times 3 times 2 factorial over 2 factorial. And then we just multiply those. 6 times 5 times 4 times 3. 360 unique organizations. So taking the 6 factorial, the number of ways that we could arrange these letters, dividing out the 2 factorial, the number of ways that these could switch, which would not be unique, so the number of ways 2 of them could be arranged. And then our answer there, 360. And again, due to the fact that I am not the greatest at statistics, I am a little trepidatious to put in that 360 because I feel like I'm forgetting something. So let's see. Okay, no. I got it. But again, even at this, I'm not the best at statistics, so my confidence is not as large as it usually is in algebra. So I take my time, but I think a little bit more through it. I slow down to make sure, and we got it right. But I wanted to make sure I was thinking through that problem correctly. And that you knew that I struggle with these sometimes too. But I have the tools necessary to get through, which is really just thinking through. This is the same thing as the last one. There's a lot of repetition in these. We want to put our reindeer in a single file line. However, Lancer and Ezekiel are best friends. Again, there's 1, 2, 3, 4. There's 5 now. So we have 5 reindeer. We have Jebediah, Lancer, Ezekiel, Gloopin, and Bloopin. And Lancer and Ezekiel are best friends. Now, I can treat them as one unit because they have to be next to each other. So we're not worrying about, oh, if one's over here and one's over here, and then they can switch around. They have to be next to each other. So really, even though there are 5 reindeer, I'm going to look at it as 4 reindeer and figure out how many different ways I can arrange them, which, again, the number of ways you can arrange a number of objects is that number factorial. So if we have 4 unique objects, in this case 4 unique reindeer, then we can arrange them in 4 factorial ways. 4 times 3 times 2, that's 24. So there are 24 different ways to arrange our blocks of reindeer. And then because we have that, again, we just multiply it by 2. So we're going to end up with 48 different single file lines of reindeer, with Lancer and Ezekiel next to each other, but also able to switch places. This is the same. So for this one, it wants me to know how many numbers between 1 and 100 are divisible by 4 or 5. So 4 would be 100 numbers between 1 and 100 divided by 4, which is 25. 5 would be 100 divided by 5, which is 20. And then if a number is divisible by 4 or 5, then it could also be divisible by 20. So we're going to find the numbers divisible by 20, or how many numbers there are that are divisible by 20, which is 5. So that's positive, that's positive. We want to take this number away because it's overlap. Think of it. 20, 40, 60, 80, and 100 are going to be in both of these lists. So I'm going to be counting them twice if I just add the 25 and the 20. So I need to figure out how many of those overlapping values are there, and that's where this 5 is. I'm going to subtract that for a total of 40, not 50. Combining those two, the numbers that are divisible by 4, the numbers that are divisible by 5, and taking away the doubles or the overlap leaves 40 numbers total. Great. I think that's it. I don't think there's any other variations on these. Sassy. And we have 1, 2, 3. Well, 1, 2, 3. Unique. Hang on. We have 1, 2, 3, 4, 5 letters. So 5 factorial ways to arrange them, but 3 of them are not unique. So if this S had switched places with this S, we'd have no way of knowing, so we need to divide that out. 5 factorial ways to arrange 5 letters. 3 factorial ways to arrange 3 letters. In this case, we're dividing out those arrangements because if these 3 S's move around, we have no way of knowing. 5 factorial is 120. 3 factorial, 3 times 2 is 6. So that's going to leave us with only 20. 20 ways to rearrange the letters of the word sassy. And then back to our reindeer again. You need to put your reindeer, Quentin, Jebediah, Lancer, and Galupin in a single file line to pull. So it's 1, 2, 3, 4. Which is, we've done this one already. Again, there's 4 reindeer. 2 of them need to be considered a single group, which leaves me with 3 unique objects. So I figure out how many ways I can arrange those 3 objects, and then I take into account that the 2 that need to be in a single group can switch places. So I multiply that by 2, we get 12. 3 factorial times 2 is 12, not 6. Sorry. 12. So again, these require a little thought. They go kind of around the bend a little bit in terms of working them. They're not straightforward. It's not just 4 factorial or the permutation or combination formula, but we can use those a little bit. You notice I never really use the formula directly. I use the factorial as the number of ways something can occur. So the name of the exercise is a little misleading, but we are. Permutations are when order is important. This is a permutation. Combinations are when order is not important, which we didn't really see any of those in this, but thinking through, a factorial tells me how many ways I can arrange a number of objects. So 3 factorial tells me how many different orderings of 3 objects that I can do. So that's what we're using primarily in here. All right, guys, one more video. So I'll see you in that one.